Okay, so today we're going to go over the circuit description of the Ding Dong Doorbell project. We'll be going over the battery saver circuit first, which is an addition I've made to the original Funway into Electronics Volume 2 circuit, so that we actually can utilize batteries instead of having to use a plug pack, because there is a constant draw on the batteries which will eventually drain them. This circuit makes sure that the energy is only there for a few minutes and then disconnects the batteries to save power, so that you don't have to go to the trouble of trying to get a plug pack in, making this circuit more versatile and making it easier to install if you choose to build and utilize it. So when the battery is first connected into the circuit, energy is present on the circuit and is powering the Ding Dong Doorbell. Now, it won't ring until the ringer button has been pressed, and I'll go over that shortly. But when the batteries are connected, C5 causes there to be a positive voltage on the gate of the MOSFET, which allows the power to be connected. But through R7, C5 is slowly charged and will then reach a point that causes the gate on the MOSFET to close, disconnecting power. So while it's in this state, it's not causing any energy draw, and the circuit of the Ding Dong Doorbell is not charged. But when the button is pressed, now the button does two things. First, it reconnects power to the circuit, and then two, rings the doorbell. Now we'll go over the doorbell ringing in a minute. Cause C5 to discharge and the circuit returns to its initial state of on. But we'll now have an off time that is governed by the resistive divider of R8 and R6. So basically what's going on here is that when you press that button, you discharge the C5 capacitor, which allows power to be reconnected, which puts a voltage on the gate of the MOSFET, allowing power to connect. But in turn, through the R6 R8 resistive divider, it puts a voltage on the base of Q1, which also then provides a discharge path for C5. So depending on how long it takes the resistive divider to provide a charge to Q1 is how long it will take for the capacitor C2 to discharge. So in this case, it's a fairly high resistance here in this area here. So we've got a 10 mega ohm to 1.2 mega ohm. This would basically be a fairly quick discharge, probably a couple minutes. But what this will do is allow Q1 to discharge the capacitor over a certain time, which will then disconnect power from the circuit. And pretty much this continues to happen every time you press the button to ring the doorbell. You press the button, doorbell rings, connects power. So if someone then comes along and presses the doorbell again within the next few minutes, it will ring and restart the on timer. But once the doorbell has been rung, power is cut and the battery is being saved. The Ding Dong Doorbell. So the Ding Dong Doorbell utilizes a 555 timer. This circuit came out in the 1970s and has been in use since then to do countless projects, used as an oscillator or sound generator, which is what we're using it for here, so that many simple things can be done. You don't need to use a modern microcontroller. You can just get a simple 555 timer, handful of components, you've got yourself a doorbell. So with the way this circuit works, once the battery saver circuit has been engaged to provide power to the Ding Dong Doorbell, when you press the button, C1 charges via D1, which in turn which also charges via R2 and R3, but it also shorts out R1 here. So the result of doing this causes what we call a click to go through the speaker, which happens very quickly. It's not perceptible, but it happens so many times per second you get an audible tone. So as the charge across C1 continues charging, it eventually increases to a point where it will trigger the trigger on the 555 is reached, and will cause the 555 to fire again. This causes multiple pulses to go through the speaker, generating the first tone. But once C1 discharges, the 555 turns off, allowing C1 to turn on again. repeating the process over and over, generating that very first tone that I mentioned. But at the same time this is happening, C2 over here is being charged via D2 here, and actually allowing for it to wait to play its part. This will happen when you release the push button. Now, normally when you press the push button, only a quick press is allowed. But generally speaking, you press it, you get the ding, and then when you release, you get the dong. So once the button has been released, R1 is once restored to the circuit, which changes the frequency of the 555 timer and allows for a lower or secondary tone, hence the term ding dong. So C2 starts to discharge via the 555 timer on its reset pin and via R4 to ground. As the discharge is occurring, the voltage drops, and quite soon the voltage drops below the 555 timer's reset voltage, and the voltage required to keep the oscillation going. So the tone coming from the speaker ceases and the circuit is ready for the next press. Now, that's pretty much, it's a very simple, very basic circuit. So, if you wish to have different tones coming from the doorbell, you can change a handful of components and get a completely different set of tones. So the components that affect both tones would be R2, R3 and C1. These affect both the first and second tones sound and length. R1 could also be changed, but it only has an effect on the second tone after you release the doorbell. The time of the first tone is generally governed by how long you hold the button in for. The longer you hold it, the longer the tone. But the length of the second tone is governed by C2 and R4. Changing these components will result in a longer time if you increase the values. So for example, if you make C2 instead of a 10 microfarad, you say make it a 47 microfarad capacitor, and if R4 is increased say from 10 to 100k, you will get a longer time of the tone and also probably a different sounding tone. And if you decrease the values, the second tone is played for less. So obviously if we reduce it from 10 microfarad to 2.2 microfarad and R4 to say to 1k, you'll get a shorter second tone. And as you can see, it's a fairly simple circuit. A lot of the hard work, a lot of heavy lifting is being done by this baby here, the 555 timer, a very versatile circuit that's had countless of uses over the years, more than I can think of. So here we have the PCB. Now this PCB is laid out differently to the original Funway into electronics, because here I'm primarily using surface mount, as you can see, batteries on the back, main components are on the front, and then of course you've got connection for speaker and bell. So bell will be where you put the push button in to ring the doorbell, and the speaker would be where the sound comes from, the actual unit. So as you can see, we're using 3 button cells in the series, which gives us the 9-volt energy we need. And I'd like to take this time now to thank the good folks at PCBWay. They are sponsoring this educational series as we learn the fun way to do electronics with surface mount components. PCBWay can provide you with high quality PCB manufacturing services, and they even have a library where you find shared projects. Now this shared project library is where you'll actually find these SME projects available for purchase from PCBWay. They will generally provide you with the boards, and there's also information there where to get the various components. Now I primarily use element 14 for that, and that's generally where I would order most of the components from. But for every purchase you make, if you use the discount link from this video, you will get $5 off on your first purchase. Plus, with each one of these Funway and SME projects that get bought, a small portion comes to me that help these videos to be made and help support me in making this content. The board will be available in that shared library when the second video comes out, which will show the construction of the board and also testing various points across the circuit. So with using my recently set up Handtech oscilloscope, I will be able to go through and show the various frequencies at where it is in certain parts of the circuit, so we can see the circuit in operation. And of course, in the second video, we'll also see it in a nice 3D printed case. The files will be available on GitHub. So please like, share, subscribe, and I'll see you in the next video. Bye for now.